Hello and welcome back. Today we're going to play a little bit with another voltage reference, and this time it's the analog devices ADR1001, and it is huge. It should be more stable than the LM399 or even the ADR1399, so that would be interesting to see. And it is sent by a viewer, Tefford from Oakland, California. Follow him. And he wanted to see it on screen, so we're going to have a look. And it's an evaluation board, and the cool thing is they did all the power supply and also the exit circuits. It's all there, and we're going to have a look under the microscope. So let's see how close I can get with the camera. Look at that. The chip itself is huge, and it is all ovenized. It is set by default on 70 degrees Celsius, so that means it doesn't care too much about environment temperature. Of course, if it is not varying too much, but 70 degrees inside. And look at it, they even built a plastic casing around it. Also, it doesn't feel any draft. You can power it here by USB or 5 volt directly. Then we have here a little IC, but we will get a microscope, another one here, another one here. You can power it also directly, but then you don't use all the regulation here. At least I think this is regulation. And well, the output circuit is not that much. It's all inside this temperature controlled area, and then the voltage that goes out here is through the bananas, all through the SMA. It is under the microscope. We are looking now through the glass, to its glass roof that we have. So let me change into the screen. Full screen of the microscope now. And we can see the chip ADR1001, and it is even the A version, the AEZ. And well, you can see the output. This is where the output goes. It is just straight, so that means all the output circuit is all inside. So we have a closer look on that. We have here 2 test points. Here are 2 resistors missing. We're going to have a look what that is. There is an LED here. We will see that later. That is when the oven is warm, the light switches off, so you know exactly when you can use it. Let's go back to the start. So this is the power section. We can power it here through USB-C or 5 volts here on the 2 pins. Here it seems like an LED, and this is an LFJW, so let's see a JN. Let's see what that does. Doesn't seem a step-up converter because I don't see too many coils or caps here. It is an over voltage over current protector, and it is the LTC 4362. And it is 5.8 over voltage threshold, so even if your USB makes a mistake and it negotiated 12 volts by accident instead of 5, then we are still good, and we keep the current under control. That is also good. And well, yeah, it's a small device. And well, here we have the confirmation. It was the LFJN. So after that, it passes through this one, a linear LTM 4048Y. It's a micro module. Let's see what that is. Okay, this is nice. This is an isolated micro module DC-DC converter, and with even a linear regulator as well. I think if I remember correct, it was a ripple or noise about 20 microvolts. So that is regulated down very nicely. And we see here we have isolation. Yeah, you want that because if you power it with USB, you don't want to have a ground loop somewhere. So this is very important to do. So we have isolated power down to 20 microvolts clean. Very good. We have here a few ground pins, it seems. And this is, by the way, not a pot. This is a screw for the board. Here we have another one, and here we have V pre and V after, so maybe this is also some regulation. Let's see what it is. LGYP. Okay, that seems indeed another regulator, but this time it is ultra low noise and ultra high PSRR do not know what that means. It's a linear regulator, and it, look at this, 0.8 microvolts. These guys are serious about their power. So here we can add something between 20 volts pre-regulator, and after the regulator we cannot put more than 16. So this one regulates between the 20, well, depending what the isolator, the DC isolator here has for output. But then, yeah, here it at least regulates down probably to 15 volts. And then it goes to the chip, but it goes on the bottom, because here we only see the output. So when I look on the bottom, we can see here a big ground plane, and we have the little one here. This is probably the positive voltage. So the power supply goes through the bottom, and then we expect it somewhere on this side. Yes, here it is, because this is that 15 volt regulator here. It goes here to the power. Yeah, and then on the top we have the output. Okay, well, let's have a closer look in the schematic. We have here the TP7, TP8, and this resistor 15 and 14. This is the evaluation board, so the resistor numbers are the same. We have here the R14 and the R15. It is unpopulated, but this is the temperature control, and you can set here by default it is 70 degrees, but you can also set it to 125 degrees Celsius, which is a lot. I don't think it will last a lot longer, so probably keeping it at 70 degrees is probably best. Here I saw already, if you keep it floating, it also goes to the default, and it has here even a power good LED. And then what about the test points? I saw the test points here, 7 and 8, and this has to do with the internally matched resistors. The point is it delivers about 6.6 volts, and these matched resistors, if you connect them the right way, you get exactly or very close to 5 volts. And the nice thing is this op amp and resistors, what you usually have in the circuit after, are also inside this temperature controlled environment for around 70 or 125 degrees. So that output circuit also is not influenced too much by the externalities. Well, here they made an example. Here you can actually see it. It is the op amp is inside this same metal housing, and the resistors are inside. You can't change them. They are fixed. They say they are specifically matched for each other. I don't know how, but they apparently calculated or just selected all these resistors just to make sure they are very close to 5 volts. Here it is connected a little bit different, and then you can also have a higher voltage out of it. But ours that we have here is made to do 5 volts. And then we go to the output. Well, as I said already, there is not much output circuit, which is good because also temperature changes will affect those. It just goes directly to 2 bananas here or immediately to the SMA. And instead of just connecting it now to the power and put it on the multimeter, I thought, okay, these people did so much effort to make isolated power, to regulate it twice, to come down to a noise level of 0.8 microvolts. And I'm just gonna connect it like this. Maybe if I cough, it already changes a little bit. So I think it needs a metal box. I ordered a few boxes in AliExpress. But measuring and really receiving it could be different. So I measured this one and it was a perfect fit. But yeah, I didn't look at the outside or inside measurements. It is too close. So it will not fit, although the height was okay. This was not it. Then I had another one because I wanted to be sure. But this is way too much. It would be possible, but I wanted a better fit. Now I had one here. That was very close to a good fit, because it probably goes. if we look at the side, that would be perfect because it sticks out on both sides. And yeah, all aluminium, easy to work with, but it was a little bit too high and I didn't want to cut too much of the pins, to be honest. It didn't feel good somehow. So in the end I ended up with this box, perfect fit in the length, enough space if we put it in like this so it can breathe a little bit. I maybe need to drill some holes because there is a power LED somewhere here and when the oven is ready there. So I will put a quick slideshow. So I ended up with this. I needed to make the hole bigger because I made a silly mistake. When this is all isolated, of course you should not connect this ground to this ground because you lose totally your isolation, and with this result. So I needed to make the hole bigger that it doesn't short circuit in the ground, and later I could put some of this liquid rubber to make it look better, but this is just a perfect fit. It goes in here, it doesn't touch any metal. I think it looks nice. I try to make the fit as good as possible and also that it on this side does connect to the ground so we have a nice shielding. The lights I didn't have a nice solution for, but we can see them exactly when we look through the holes, and because it's sort of a Faraday cage I think it will be okay. Here I will put later some liquid rubber around, first some shrink wrap and then the rubber. Now we're serious with shielding. I also want to be serious with the SMA, so I will do this with the coax like this, connect to the meter there, and of course a shielded USB. Let me see, I want to show you the lights. So hopefully I'm at a good angle. Here we go. Do we see the lights? Yeah. It's warming, it's warming, it's warming. Bloop, off. So now the 70 degrees is already met. Of course it needs to stabilize still a little bit. It has been on for a while. The light is green. Of course the red one went off already more than half an hour ago. So let's see. I am on one PLC. Usually you would be a little bit slower. So this is like 50 samples a second. The signal is quite smooth. You do see a little noise, but we zoomed in like a crazy lot. So let me see here. Let me reset. And then we're going to check here. So that little noise that you saw is peak to peak 3 microvolts, which is like nothing, and the standard deviation is even below the microvolt. And I think if we use like 10 or 12 PLCs, like 5 times a second, they advise you to do even lower, then you get even better readings. So we did 4,000 readings and we are here at 4.577 peak. Standard deviation here is 685 micro. Let's try and do the same with 10. And one thing we are really like nitpicking, or how you want to call it, because if I look here and I even use the same USB connector, I plug in now something else in my same USB hub. Look at that, you already see a change. So it becomes really sensitive. So the power supply is very important. even though it's isolated, even though they have these low noise regulators, you can still see these little changes, but we are really in the microvolts. What I wanted to do is set the PLCs a little bit different. Let's try this with 12. I'm not using a filter, I am using auto zero. And we see already that the noise becomes less. I want to see that in statistics. We start again. Well, clearly this takes a lot longer, but it's stabilized sort of. I don't get any big changes anymore. So I did now about 200 readings instead of those 4,000, but we see already it is a lot lower. This is not because the reference got more stable, it's also because the multimeter itself also has its error, and especially when you start to measure very fast, the error becomes higher. And maybe I was close by too much, because now it jumped, because it was around 1.9 and now it had a little jump, but I will just write these down. These values are a lot lower. I have a few for reference. I have here the LT1021, that is the one that is in the DMMcheckPlus here. Compared to a lot of other references, it is actually very quiet in distortion and noise. I have here the LM399 boxed, that is this one. I have the ADR1399, that is this one from Releted here. And I have the ADR1001, that is here in this box. That's the one it is about. So when we look at the distortions, they say here what the noise level is. They say here it needs to be 3. It was running on batteries. And I come here with one NPLC. I come here about 6. But then I also get the noise from my multimeter as well. And this was the standard deviation. This could also change when the device is not completely heated or not, so then you have something here. But the standard deviation, that is kind of an average also over all these measurements. At the 1 ppm I had like 4,000 measurements, and 12 NPLC I had 2,200 measurements, and the time was about the same. And then when I do the 12 NPLC, we see a lot better values. Weird enough, the deviation came up instead of going down, so that surprised me a bit, but I did it multiple times and it is what it is somehow. Then I did the box, this one, and here we saw a difference between a simple USB wall charger or the linear power supply. It went here from 8 to 7, and here in the deviation also it slowly dropped. But then we see here a difference in the longer scan with the 12 NPLC. We saw it drop down from 1.3 microvolts to 0.72, so that was a nice drop. And then when we look at the Releted here, the ADR1399, and we are measuring everything here, because it is including the power supply, including the op amp, because this one also has an op amp to get the right voltage that you want. I put it to 5 volt. So there is a conversion also. You also have that noise. Here it was 5 and 0.7, which is pretty low, especially when we see here that it is 1.8. Here we are closer to that 1.8 with the slower scan, and here the noise is even lower. So well done here on they did a good filtering. And I don't have the LTD set, but I just wanted here to see the price difference, because the LM399 you buy for around 18 euros. While the LT set 1000 is 48, and the ADR that we have here is already above 100. But then, yeah, you see different values also. It's the lowest distortion we see here. I also tried with the wall charger and with my linear power supply, and as I said, everything matters. But you see already, because of the good filtering inside with the isolator, with the low noise amplifier, you really see that it does make a difference, because here it's a huge difference and here it is very close. Almost it doesn't matter anymore. And here we have with the lower scan, and then we have really interesting values. Look at that. So nice. But I'm surprised in these values, everything matters. The type of USB cable you used in the beginning. I did these measurements many times. So this is also an average. First I took out the outliers, and then I took an average from those values that I measured, because in the beginning I was using a simple USB cable, and then when I touched the cable I already saw that it was a microvolt up and down. So then I took better cables. Also for the voltage I used the coax cables here, also to make sure there is not too much distortion also on that. Then later I changed from a normal USB charger to this linear power supply they used for audio. It just has a simple 7805 or something, so that also has already a little bit distortion. Even though it has filtering and everything, it is very difficult to get a good clean power supply. So thank you very much Tefford for letting me play with this. I hope you are not disappointed with the casing I built. I'm quite pleased with it myself, and thank you for watching, and I hope to see you next time.